you engineer inherently to help society. So society is going to influence your engineering, right? We make things to help people, right? And so we're not making things to not help people. We're making things to kind of change society for the better.
Yeah, thank you,
You're welcome.
Dr. Jones, for being here in the podcast. Dr. Jones is a distinguished professor, and he's the creator of a course called Impact of Materials on Society, which was developed for all UF majors and was given, for example, the 2018 National Award of the most innovative class in material science, and many, many wonderful things that you've told me uh, previous to the
Oh,
conversation.
thank you very much
And
for coming.
yeah, so maybe we can just start right into it. So
Okay.
why are materials important, or kind of why you created? What was your thoughts when you started creating the course? What drove
I
that
think the thing
inspiration?
that drove me the most was I saw a lot of students taking or being required to take core classes in humanities and sociology and not understanding why they had to take those classes. They weren't making the connection between that class and what they were doing in engineering. And so I thought, well, maybe we can create a class that helps to tie that together, that helps them understand that these humanities courses and these sociology courses and the anthropology courses are actually really important if they're going to be an innovative engineer down the road. And so, and at the same time, I also thought maybe there's a way to help non-engineers understand what engineers do. So I reached out to Sophia Acord, a professor over in the humanities area,
And
and said,
she's an
"Do
anthropologist, you said?
well, no, she's actually a
As-
humanities
Oh, just humanities.
professor,
Okay,
but she's
cool.
now actually the associate dean of research in the College of Arts, Fine Arts. But anyway." And I asked her if she wanted to do a class together. Basically, I said, you
Hmm.
know, and she said, yes, that sounds really exciting. She was teaching technology and society at the time. And so we got together, and then she started inviting a lot of her friends over there that were in area from anthropology to English to sociology to humanities. And we got together and we brainstormed on a sort of a modular class where each week we would take a different material and we would talk about the science behind that material, but then also the social impact of that material, and then we would take those and move it down the road into looking at what the future materials might be. So, for example, if I did plastics or polymers that week, then I would talk about how polymers form and plastics and how they're engineered and everything else. But then on Wednesday, we brought in Marcia Bryant, and she talks about Brownie Wise and the birth of Tupperware, and why Brownie Wise was so instrumental in marketing Tupperware, because Earl Tupper had made this product and couldn't sell it to anybody, a Tupperware container, and he thought it was good for nuts and bolts on a workbench.
Hmm.
And she came in and said, let's have a Tupperware party, demonstrated how it could be done, marketed it, it exploded. She understood the ramifications of it. So the whole idea of how you market something. And then we look at a future material like biopolymers, or replacing conventional polymers, right? Biosourced polymers, to try to make something that's going to be more sustainable. And then what we do on Friday is we flip the classroom and we have the kids basically create an advertising campaign for, say, bicycle helmets out of biopolymers. So they have to think of the biopolymer and they have to think of what the marketing campaign would look like for that. And they have to target different audiences. So like one group might target mothers and others might target BMX kids. And they have to think of how they're going to market their biopolymer helmet to those different groups. And so it gives them an idea of understanding just how the social aspect of that process is so important to the engineering side of everything. And and then the next week we go off and study another material, steel, and we talk about Andrew Carnegie and creative destruction. So each week the goal is to give them not only an understanding of a new material, but also a social principle that we give them in like a toolbox they take home with them. And so at the end of the semester, you've got 12 different social principles that you can apply to any problem: creative destruction, entanglement, all these things that allow them to sort of broaden their thinking outside of just, I need to solve this engineering math problem and I need to crunch this thing away, to, wow, I need to understand why my innovation might be important to society and how society is going to affect my innovation. And if they understand that, then it makes them just a more socially aware engineer, right? Their chances of succeeding go way up. And so we spent a lot of time. It's been a lot of fun creating this class, and and it seemed to have struck a chord. A lot of universities, uh, Boise State, Michigan, a whole bunch of Case Western are all teaching this class now, and now it's kind of going international. So they really, the latest has been we've been working very closely with the continent of Africa and the universities down there because they're still sort of establishing their materials programs. And so they're still trying to, each university, they're trying to develop what the curriculum should be like. And so the United Nations has put in their preliminary plan to have this class be one of the core classes for that, for all the universities teaching materials in Africa. And so we've been taking a lot of, doing workshops down there in Botswana and Tanzania and stuff like that to teach the teachers how to teach the class. So we put everything for the class up online. We wrote the textbook. It's free to everybody. It's an open source textbook. We put all the materials online. We put all the lectures, videotapes of everything, all the tests. Don't tell the students. Anyway, everything is online, and the goal is to make it as easy as possible to just pick this thing up and plug it into your university and start teaching it. So it's been fun.
Yeah. So could you? Maybe we can go also a little bit deeper into
Sure.
the materials themselves and you called them the social impact or the
yeah. So for example, if I'm to give you an example, the one I did recently was if you're talking about steel and iron. Okay, so we all know what steel and iron is, and we know that it's impacted our life. But so I would teach you how we make steel and iron and everything else, and we have fun in those lectures. We do demos and we make stuff, and then the social science lecture for that week is Andrew Carnegie, the story of Andrew Carnegie and the birth of U.S. Steel. Mm-hmm. And what he did was he exploited something called a Bessemer furnace, which basically said rather than taking a material that you're going to when they made steel before then, they would stick a rod in there, they would turn it around, the guy would taste it and look at it and smell it and everything else and go, it's just come to steel. It's now come to nature, right? And you made little tiny batches of steel. Well, you're not going to make railroads that way. And he came in with a blast furnace and blew air through it and created steel in 15 minutes and tons of steel. And suddenly he had this mass production. But it put all those people who were called puddlers out of business. So there was a creative destruction. You create something, and when you create something new, you destroy something old. And so you have to think about what your impact is on society there, right? So in this case, he put a lot of puddlers out of business, and that became a problem. And so how do you address that? And so then the future material for that week is magnesium. And so we talk about how magnesium is replacing steel because it's so much lighter. And it can be used for all sorts of interesting applications. And then what they have to do is they have to create a product using magnesium, but think of the creative destruction challenge that's faced with that. So the example I love is that I had a group who said they wanted to make drones for the movie industry out of magnesium. And I said, that's great. And so
How
why?
about the cameraman?
Yeah, exactly. And you wind up with you're displacing the cameraman. And so what do? You teach them to fly your drones. And if you teach them to fly their drones, then they have all the contacts in the movie industry. So that's and so it's now all of a sudden you're not just making a drone, you're making a drone that has a dedicated audience. And so that's by understanding your creative destruction challenge there, you're also creating a product that has a much greater chance of being successful. And you're giving them a job, right? You're giving them a new opportunity. You're retraining them in a new area. And so recognizing that when you destroy something or you're displacing people, if you can work with those people to retrain them into your new product, then they're going to be much better off, right? And you're going to be much better off because they've got a lot of contained knowledge in their background. And so that's the social side of it, right? It has nothing to do with making a better product.
Right.
It has everything to do with understanding that you engineer inherently to help society. So society is going to influence your engineering, right? We make things to help people, right? And so we're not making things to not help people. We're making things to kind of change society for the better, hopefully. And so, and every week it's a different material. And so we do aluminum. And when we do aluminum, we talk about the birth of Alcoa and how Alcoa was a company that was basically found to be in violation of antitrust. They were seen as being a monopoly, but they were not a monopoly because they tried to buy everybody out. They were just really good at what they did, right? And so they became a monopoly. And so understanding in that week, it's all about intellectual property and monopolies and how do you deal with this, right? So if you create something, do you make it a trade secret like Coca-Cola and don't tell anybody about it, right? Recognize that if somebody figures it out, they can go off and make Coca-Cola, right? Or do you patent it and recognize that you're going to have that patent for 17 years or whatever, and then you're going to lose that patent, but you also have to enforce that patent. And so how do you address your intellectual property when you create something new? So when you create an innovation, how do you want to address that? And there's no right or wrong answer. Right. Everybody has a different way of doing it, and they might do it for very different reasons. Some people will say, no, I'm going to patent it, but I'm also going to license it to anybody who wants it, right? You see this right now with the COVID vaccines, right? Do you patent that, and do you protect it, or do you share it with third world countries, so that they can have access to it? And how do you deal with the patent rights? You have an obligation to your stockholders, but you also have an obligation to society. So teasing that out is interesting. So every week it's something fun and different.
Yeah. So for example, in that specific example, I think it's pretty cool that you teach that, because something that I was thinking is that these lessons on society can be applied to not just material sciences, right?
No, this is all engineering. All engineering.
And it can be like, for example, computer science. For example, I was thinking of the examples you were talking about, monopolizing an industry, and when something new is created, which is inherent in when something new is created, you're the only one that has it, right?
That's right.
You're technically a monopoly, right? So for example, are you aware of DeepMind? DeepMind is this company that they do artificial intelligence, and they created this new artificial intelligence model that basically solves protein folding problems.
Okay.
And they solved this problem that has been like a decades-old problem that no biologist has solved before, and they feed a lot of that data into the model, and they were able to solve this problem and with performance that no biologist could have ever done before. And what they did is that they just released it to the public. Right? They did the analysis, or at least how the CEO puts it, is that they did the analysis of how is this product can be the most beneficial to society.
Right.
And they decided that, at least for that specific product, the most beneficial could be to just release it to the public.
Sure.
And that has been used for many companies and researchers and whatever to start having this tool to solve their own problems.
Yeah, absolutely. And so sometimes that's exactly what you'll decide is that it's better in the end to go ahead and release it and let it go out there and recognize that it will help society as a whole, and you will make your money somewhere else, right, along the way, right?
I think so.
And so, and it will come back to you, right, in ways that you might not expect, but it does help you generate that sense that you're doing something good for society, and that's I think a very strong sense amongst a lot of innovators these days. Is that it's not all about the money. It's about doing something that actually makes society better, and that's really cool. I think that's awesome.
I think so.
Right? Yeah.
Yeah, and I think as you were saying, for example, the main purpose of a company is to make money, right?
Sure.
But just solely thinking about making money can like shield other opportunities that might come as...
Well, it's interesting, right? Just look at Andrew Carnegie, right? He does this. He becomes the richest man in the world.
Yes.
Right?
Yes.
And then what does he do for the last 20 years of his life? He sets up foundations and gives his money away.
Yeah.
Right?
Yeah.
So the Carnegie Foundation, the Carnegie schools, everything else, right? So in a sense, it's almost like they recognize that money for money's sake is not the end goal, right? Look at Bill Gates. He's spending vast quantities of money trying to help better society, right? Help cure certain diseases and things like that. And so I do think that people, recognize that later in life, and sometimes they get it earlier in life too, and they realize they don't have to wait till they're old before they can start giving everything, setting up foundations and doing philanthropy. And so, but no, it's really interesting. I mean, we even do one like on paper, which seems like really crazy, but we talk about information storage, which is much more computer science, right? But then what the lesson there that we really tease out is this idea that there's a right to be forgotten. So it used to be that if you did something egregious, say whatever, you shoplifted when you were a kid, right? And then no one would ever know about that. But now people can find your records when they do a Google search on you and find stuff, right? Well, we tease out this idea of how egregious does it have to be before you have the right to say, no, I'd like that expunged. I'd like that be taken off the internet, right? So it's not common knowledge, because it was just a childish mistake versus, I killed somebody, right? Then obviously that shouldn't be expunged. And so there's gray levels all between. So we talk about this kind of the right to be forgotten and who makes that decision. It's made, interestingly enough, it's oftentimes made by the editorial board of newspapers. So the newspaper sits around and decides, do we want to take this story down from our previous publication 15 years ago, or do we want to leave it up, right? And that's decided, and that can impact someone's life all the way through their lives, right? If that's still there. And it was never an issue when it wasn't digital. But when you start shifting your information storage from paper to digital, suddenly it has a different lifespan to it, and you have to think about what the implications of that are, right?
And do you have a material science example for that, or like?
So what we talk a lot about, I mean, the material we're talking about in that case are how you went from paper, or I mean, originally clay, right, and hieroglyphs, to paper to digital storage, to semiconductors, right? And so we talk about how you store information digitally in semiconductors, and then the creation of the cloud. And so what are the materials that were involved, and what are the materials innovations, right? The silicon processing that you had to go through to create the random access memories and the permanent memory cells, right? And the magnetic storage, et cetera, that would allow all this information to be stored in massive quantities, right? Digitally forever, right? So behind the scenes, there's a hardware, right? The software is the cloud, right? It's, it's stored on the cloud somewhere, right? Well, the cloud is a bunch of servers that are operating silicon chips, right? That are operating trillions of transistors. So recognizing that, I mean, it's obviously important. And we have, virtually every piece of data now is digital. I think it was around 2002 or something like that. We started having more information stored digitally than we had written, right? And ever since then, it's exploded, right? And so, with all the video and everything, is no contest. And so but with that comes a price, right? And so we tease out that part and that one, and the semiconductor. When we talk about delegation, what do you delegate to your electronics now that you didn't before, right? We delegate the ability to drive around, right? If you get to a new town, you just Google where you want to go, and your map shows you, and you just drive. But kids people have no idea whether they're going north, south, east, or west anymore, right? They don't read a map. They just follow the directions on their phone. So they have delegated that, right? And so we're starting to delegate more and more, all, telephone numbers, names, all sorts of stuff that we delegate to our phones, so that and it's not a bad thing. Right. It's just recognizing that it's a social change, right? That we spend a lot of time delegating stuff to our cell phones and recognizing what do we want to keep to ourselves, and what do we want to go ahead and let the phone handle for us in the future. So you're kind of becoming symbiotic with your phone, right? And recognizing that is kind of fun, because students don't really think about it all that often. Sometimes you delegate, and we talk a lot about what you're doing with your phone, right? What do you're delegating your whole relationships to phones and things like that. So it's interesting. So it's not just the software of how we're going to get to stay on Moore's law and understand how you make better transistors and everything else. That's the research I do personally. But it's much more about, okay, if we stay on this, what are the implications down the road as we become, more and more dependent upon AI and dependent upon computing power to do things for us.
And what does it take to start thinking like that? Is it just extrapolating the thought of what has been, what could be?
I mean, I saw that one example today, it was a couple of days ago, right, where somebody won a digital art contest using an AI program. Remember? I don't know if you saw that. And they painted a painting, right? Well, you're now delegating your art to a computer, and the computer is generating that, right? Or the computer is generating. And it's not a bad thing. It's just recognizing that this change is happening, right? And some people are going to fight it and say, no, I don't want to do that. And some people are going to say, wow, it's really creative. I thought this was, inspiring, right? And if art is supposed to be inspiring and you're inspired by that art, then does it matter what the source was, right? And so you have to kind of just recognize it as it's changing, how it's influencing you. So, so the class touches on a lot of different things. But it's a lot of fun to teach. And so.
I definitely think you should at least start pushing, and maybe you have, for other engineers, right?
Oh, absolutely. No, it's not just materials. This is all engineering.
Yeah, because, for example, I do robotics, and robotics is always the constant question that always people ask is, well, are you replacing this
Right.
person? Are you replacing that type of worker or
Right.
whatever? Like cashiers or waiters or
Right.
waitresses.
Right.
Yeah. So
And they always see it as a negative thing, and
Yes.
it doesn't have to be. Right. You see the stuff in Japan, right, with elder care being, delegated to robotics. And so, no, this class is not even just for all engineers. It's for all students in general at UF, right? It's a freshman class. It doesn't require you to have any great math skills other than high school math or high school chemistry. So in that sense, right, I love it when we get the anthropologists and the English majors and others taking the class, because when we break into those small groups of 5 and they solve the problem, if you've got one of them in there, they bring a very different perspective potentially, right? Now they're not so far down the road that there's this big differentiation between an engineering student and a non-engineering student. They're freshmen, right? Or by and large, but sometimes you get sophomores and they bring a very interesting perspective to the group. And so I think that's really, really valuable, because I think engineers have to hear that. They have to understand that perspective could really enlighten the conversation.
Yeah, and they'll probably have to deal with that later in the road.
Yeah, right.
Like
Absolutely.
Really
Absolutely.
Into a company, they'll have to deal with
right.
non-engineers.
Or they may have a company and the company has nothing but engineers around the table, and they may say, we need to bring somebody who's a non-engineer into the room and see what see what their perspective is on this thing, because we may be missing something completely, right? And a lot of companies have gone completely belly up because they missed something that was a very simple social challenge, right? That they didn't recognize it. So I think that's the idea, is to say there's room for everybody at the table, right? And we need to make sure that all these voices are heard, right? So that you recognize the ramifications, and of course that includes diversity. Diversity both from all perspectives. So,
and maybe do you think I was gonna say that one of the cool things that I've seen you kind of like promote the class is with your own Instagram. And with your own Instagram, you posted some.
Oh yeah.
You created some posts of materials and how materials has been shaping society, on how some materials has some application that maybe one doesn't know. For example, I wrote a bunch of them, like nanoparticles of iron oxide that they've been used for many things. For example, like trying to treat tumors in the bloodstream. And I think one of the University of Florida's professors are working on that, right?
Mm-hmm. Yep. That idea of hyperthermia. Somehow you can get a iron particle to oscillate in an RF field, right? And if it starts to vibrate in an RF field, then it'll actually start to create heat. And so if you can target it so that it'll accumulate in a particular tumor, then you can heat up that tumor. And you don't have to heat up the tumor very much before it'll kill the cells in the tumor without killing the surrounding material. So that's the idea of magnetic hyperthermia. So I think there's a lot of interesting, I tried with some of those Instagram posts to try to pull out some examples that I had personally been familiar with in terms of things that I thought were really cool and innovative. But it's hard to write those things.
I bet.
Yeah, you spend a lot of time kind of cutting and pasting pictures to put it all together in an Instagram post. So.
Yeah, but you had really good ones. For example, I have titanium oxide, magnesium, concrete, gold, glass, ceramic material, bioglass. Is there any of those that I mentioned that you kind of like?
Oh, I mean, I think the Bioglass one always struck me as interesting, because when I was an undergrad here at UF, I was working in a lab with Dr. Hinch, who is the creator of Bioglass, and working with him.
Okay.
Yeah, so he's the guy who invented Bioglass that went on to become NovaBone and NovaMin and everything else, right? And so I was just a.
And would you mind explaining what is ceramic?
Oh, sure. So Larry Hinch was a really interesting guy. He was coming back he was actually on a plane. And he was flying back with some people from that were a general who had been in Vietnam. And he said, you want to do something really helpful. The problem we have is these kids are getting wounded in the legs, and they're having to have their hips replaced. And when we replace the hips with a titanium hip, it falls out after 4 or 5 years, because the body just doesn't like to have metals in it. Bullets, swords, whatever, and so it rejects it. And so he said, if you could create a material that would actually not fall out, that would be really innovative. And so Dr. Hinch, who was a ceramist, said, well, maybe I can come up with. So he took the components of bone. He knew the components of bone were potassium phosphate, silica, sodium, whatnot. Added them all together, added a little sodium, and melted it into a glass. And he made this beautiful glass, and he called it Bioglass. And so then he took that glass and he took a little piece of it, and he made a little rat femur, and he stuck it into a rat's femur. And he came back like 2 weeks later to take it out, and he couldn't get it out. And it was weird. They looked at it carefully and realized this was the first man-made material to bond to tissue. No tissue had ever bonded to a material. So they were trying to figure out what in the world had happened, right? And so of course they said, well, this is perfect. Now I can make a hip out of this thing, right? And it will bond to the bone and it won't fall out, right? When you stick the hip into the ball into the femur. Well, the problem is that it's bioglass. It's glass. It can break, right? So you don't want to make a hip out of glass. That's not very good. So they tried all sorts of crazy things like bonding it onto the surface of metals and things like that. But they kept studying it. And one of the things they did with it was they used it to create a little tiny bone that replaces the anvil, stirrup, and hammer in your inner ear. And there are about 5,000 kids a year that are born without. They can't hear because they're missing those bones. And by putting this thing in, it bonded to the cochlear nerve and bonded to the eardrum, and it restored their hearing. So that was pretty cool. And then they were still trying to figure it out. And there was another guy named Jim Adair here who was working on why your teeth are sensitive. And it turns out they're sensitive because you have pores in your teeth and you start conducting ions down to your nerves and you go, yeah. And so anyway, when you drink something that has lots of ions in it. So Larry Hinch said, well, you know what, maybe we should try is if we coat the teeth with Bioglass, maybe it will help regrow the enamel. And it sure enough, it did. So the enamel regrew on your teeth and it covered up the pores and it stopped your teeth from being sensitive. And so GlaxoSmithKline bought the patent rights for Bioglass for like $70 million. I think Larry got like 10 grand out of it because by then it was all in lawyers. But anyway, and they put Novamin into all of the Sensodyne toothpaste. So now if you buy Sensodyne toothpaste, if you look at the ingredients, one of the ingredients in it is Bioglass. And the idea was that it would actually help your teeth become less sensitive because rather than just deadening the nerve with like one of the cane drugs, that will just deaden your nerves, which is what traditionally something like Sensodyne does, now you regrow the enamel. And so it will plug up the pores and it'll stop your teeth from being sensitive. So it repairs your teeth. So anyway, so they tried to figure out why it was doing this, and it turns out that it actually triggers. It's really weird. So they took a bone, they hollowed it out, they packed it full of Bioglass. They came back a year later, and all the Bioglass was gone, and all the bone was completely redensified. And so they said, weird. So what turns out happens is this Bioglass, when it's in the body, it starts to decay, it corrodes. And so it releases all these potassium and silica and sodium ions. Well, in your body, you have these things called stem cells. You've heard of them, right? And when you're about your age, you have the most stem cells you'll ever have. Every year, every 10 years, you lose a decade. I'm down to like 3. But anyway, but these stem cells, when they reach an environment where all these potassium and silica and sodium ions are evolving, they convert into an osteoblast. So it actually triggers a genetic reaction in your body to turn stem cells into bone cells. And so it's the first man-made material to ever trigger a genetic reaction in a body. Oh, wow. And nice. So that's how Bioglass works. So when you put it into an interface between the bone and you coat something with it, it will decay and the bone will grow into it. And so that's why people are really excited about it. And so anyway, so that's the origin of Bioglass and where it's gotten to now. So now we understand the problem is you really can't solve. So we thought osteoporosis, we can solve osteoporosis with this. But the challenge there has been that if you get old, you don't have very many stem cells left. So you don't have the stem cells necessary to grow the new bone cells, right? So you really have to think about how you're going to trigger other stem cells in your body, adult stem cells or something else, right, with Bioglass. So they're doing a lot of studies on this, and they continue to try to figure out how to make Bioglass continue to. It's amazing. They've studied probably, I don't know what it was, 10,000 different combinations of the elements that go into Bioglass, right? So you have silica and you have sodium and once you potassium phosphate, and once you put it all together, you can come up with all sorts of different ways to ratios, right? And if you add too much of this and too much of that, it's no longer bioactive. So there's one little region where it's bioactive. And in fact, the very first combination that Dr. Hinch tried is still the most effective of all the 10,000 we tried. So it's amazing. And the man was a genius. But anyway, so, but yeah, it's a pretty neat innovation. So
Apologize.
Anyway. But yeah, it's been ranked as like one of the top 10 inventions of ceramics of all time.
Oh, wow.
Yeah, so it's been highly, highly recognized. Anyway.
Cool, and that's pretty interesting problem because it involves many areas. That you have the biology side, you have the mechanics side, as you were saying, if it's made of glass. And is that kind of how material scientists are starting thinking about a problem, like grabbing the chemistry, grabbing the physics, and
yeah, I think that's a really astute observation. Material science is kind of like applied chemistry or applied physics or applied mechanics or whatever, right? So it pulls from a lot of different disciplines. But I always like to say, if you're an engineer, you're going to make something, and you have to make that something out of something. And we're the people who study what you're going to make it out of, right? So if you use the right material, you're going to become rich and famous or whatever, and you use wrong material, it'll probably blow up or something like that, in which case you'll be a phenomenon on YouTube or something. But anyway, the bottom line is that you have to draw on your knowledge of chemistry and physics and engineering and all of that stuff together to try to create new materials that do new things, right? And so we continue to work at those interfaces. So we have people in material science that are way over in the bio side and working with stem cells and the biological sciences. And we also have people that are over in other areas that are working in, much closer to physics, right? On new ways of doing memory for, or topological insulators or things like that. And then you've got other people that are working more in metals and stuff like that with the structural people, right? And they might be working with aerospace engineers or something like that. So you're always kind of working at these interfaces. And always, all the neat stuff happens at interfaces, right? So it's always the confluence of two things, whether it be sociology and engineering, or whether it be physics and material science, or whatever it is.
Right. And you're personally working on, as you said, semiconductors.
Yeah, my personal thing is trying to figure out how to continue to make chips faster and smaller. So we work on what's called front end processing, what you do at the beginning. And it's really kind of a crazy problem. It's like the analogy is we're trying to make the sweetest sweet tea ever made, right? We're trying to when you have a semiconductor, it inherently doesn't conduct electricity. But if you add an impurity, it will start to conduct. And you can add a little tiny bit of an impurity, but the impurity has to be soluble. It has to be dissolved in the silicon for it to be conductive. And so when you add too much of an impurity into anything, right, it will precipitate out. So if I add too much sugar to my water, I'll make rock candy. I won't make sweet tea.
And if you don't mind, first, really quick, to explain what are semiconductors and what are they used for?
Sure. Semiconductors are, here.
You have one
here? Yeah, sure. It's got wafers lying around here.
And also, if you have some sort of water, I think the throat gets really dry.
Yeah, I've got some water. So these are...
Okay.
So these are semiconductors. This is a patterned one. Sure, let me get it out of here. So that's a...
Thank you.
Sure. So it's a processed wafer. I mean, it's a smaller one, but it's a processed wafer.
Yeah, you can get it into the camera.
So when you make a computer chip, they're very light. You're using a material that's silicon. Yeah, silicon. So this is the element silicon. So element silicon is it's sand. SiO2 is sand without the oxygen. So if you take the oxygen away, this is what you've got left from sand. So you start with sand, to make a silicon wafer. But when you're done with it, you have to purify it. So it's very, very pure. There's less than, the amount of impurities in this thing are probably less than 1 part per million or part per billion. Probably part per billion. And so it's a very good insulator like this. Won't conduct electricity. But if I add just a fraction of a percent, I can change its conductivity 10 trillion times. I can take it from being a really good insulator to being a really good conductor with just a little tiny smidge of an impurity, like boron or arsenic. So The challenge is that that's how you make semiconductor devices, is that you add little bits of impurities where you want them to, you pattern them and you put them in, and then you can write where the electric current goes. Okay? So at a very basic level, that's what semiconductors do. And then all you do is add more layers on top of it to figure out how you're going to address all those different little devices you made. And in the end, you wind up with a device, a little square like that thing, right? You see the repeat units, right? Each one of these 4 squares right here is a logic device that would go into your computer or your cell phone.
Right. So those are the chips that people talk about.
And that's what chips everybody talks about. So then you put it inside of a package, and you wouldn't even recognize it, right? Because it's all inside of a big metal hunky thing that keeps it from getting contaminated or oxidized. But these things contain right now, the best chips contain about 100 billion transistors in that little 4 squares, right? And so they're trying to get to 1 trillion. So that's the goal, is to get to 1 trillion transistors. But right now, it's about 100 billion. And that's in one little area, right? See, these things are so small that they are literally like 30 atoms across, you know, so you're getting smaller and smaller in the region. So actually they kind of stopped, I should correct that. They stopped making the device smaller a few years back, but they just started packing them in more. But and so they probably stopped at around maybe 170 atoms or 150 atoms. But anyway, my challenge is that when you try to stick a metal onto a semiconductor, it doesn't make a very good contact. And so there's a resistance to putting the current into the semiconductor and a resistance to getting it back out. But I have to do that to be able to address the device. I have to be able to put a current in and come back out. So that contact, right, between the metal and the semiconductor has to be as low in resistance as possible. Because if you take 1 trillion of these things, or 100 billion of them, and they all have a little bit of resistance, well, guess what happens when you have resistance? You get heat.
Okay.
And so if you ever wondered why you can't have your laptop in your lap anymore, it's because those 100 billion transistors are all getting really hot, right? And as they get hot, they heat up your lap, right? And they also chew up your battery, right? Which makes your battery life die. So somehow I have to figure out a way to make that contact really low in resistance. Well, how do I do that? I need to make the semiconductor look as close to being a metal as possible. Then I have a metal-metal contact. That's really low, right? If I hook 2 pieces of copper together, I've got a really low resistance. So I have to dope or add as much impurities into the silicon as I can. But the problem is that if I add too much, they precipitate out, and I get rock candy, right? I've added too much sugar to my water, and so what do you do if you want to make your sweet tea sweeter? So this is a good question for you. If I told you to make you want to make good sweet tea, right? You have 2 ways of doing it. You make the tea, you put it on ice, right? You make iced tea, and then you add sugar.
Okay.
Okay. The alternative is you take the tea, you make it, and while it's still super hot, you add the sugar, right? Which one's going to make a sweeter sweet tea?
I would have to, because when it's cold, the atoms are closer together. Right? Or at least they have less disorder than when it's hot. So,
but think about solubility, right? We're talking about...
Okay, yes. Yeah, I was not the greatest chemistry.
All right, so when it's something cold, have you ever added sugar to cold tea, right? What do you wind up seeing? You see all the sugar sitting on the bottom of your glass.
Okay.
You keep having to stir it, right? Okay. And it won't go into the solution.
Yeah, correct.
If it's hot and you put it in there, you stir it once and it's gone. It's all dissolved.
Is it just because your solubility changes?
Yeah, the solubility is always greater at higher temperatures.
Okay.
So I can always dissolve more sugar into my water if my water's hot. So the key is add the sugar, then add the ice. Don't add the ice and then add the sugar. So the order makes a difference as to how sweet you can make your tea. All right.
Okay, that's what you said. You're the front end problem.
Right. So when I'm dealing with a semiconductor, what I have to do is make sure that I add my impurity and get it as hot as possible, right? So that I can put as much of it into solution as possible. Okay. So I'll make the contact as low in resistance as possible. So we're going from heating it up to 800 degrees C, the stuff to 900 degrees C, to 1,000, to 1,100, to 1,200, to 1,300. It's that melted 1,400, so we don't want to go above melting point, or it will just turn our wafer into a puddle. But we have to figure out how close we can get to that temperature. And now the problem is I also have to keep it really thin. So if I go to the higher temperatures, the diffusion happens real fast and goes real deep. So what I have to do is make it shorter in time. So I go from hours at 900 degrees C to minutes at 1,000 to seconds at 1,100 degrees C to milliseconds at 1,200 C
Oh, wow.
to nanoseconds at 13 or 1,400 degrees C. So I'm trying to get highest temperature as possible for as short a time as possible so I can dissolve as much into it as I can.
Oh,
and
wow.
that's what we study. So we do a lot of laser processing where you're dealing with time frames that are on the nanosecond time scale
Okay.
to try to get that semiconductor to be as low in resistance as possible. So it's a really interesting challenge of how the games you play, right?
Yeah.
And they want to all go to very low temperature processing. So everybody wants to keep the processing now of all your devices super low.
Mm-hmm.
But that means my solubility is terrible, right? Because I'm now at low temperatures. They're insisting on adding the ice before I add the sugar.
Mm-hmm.
And I'm like, well, that's not going to help me. So I have to figure out new tricks to get it to dissolve in high concentrations at low temperatures. So we study a lot of stuff like that. So that's what my field is about. So
Okay, pretty interesting. Yeah.
anyway,
And how do you start adding the soluble?
so we do that with
impurities?
a process called ion implantation. So you actually implant, you take the ions that you want, say boron or arsenic, and you create them in a gas, and then you charge them and you accelerate them at a very high speed, and then they bombard onto the surface of the wafer, and they penetrate a certain distance, just a few hundred atoms deep into the surface. And now they're all sitting there randomly. And so that's why you have to heat it up, because you have to turn around and shake the lattice and get them to go onto the lattice sites. And when they do that, they become active. So I use ion implantation, a big tool, 3 times the size of this room, right, to accelerate and blast the surface of the semiconductor. And then you take a furnace or a laser afterwards to activate it. So it's kind of a 2-step process. And so, so that's how you have to do it. Now people
you have to do both simultaneously.
you have to do both, one and then the next. And so there's a problem. The acceleration and the introduction has been solved. We know how to do that. We just don't know how to activate it very well. And that's one way of doing it. The other way is to just literally grow the semiconductor with the impurities already in it. So now you have to grow it selectively. So some people are doing growth, and we just study that, and some people are doing implantation, and we study that. So 2 different ways to dope a semiconductor. You can either add it after you've grown the semiconductor, or you can add it while you grow the semiconductor.
Okay, interesting. Okay, so maybe having said all what your research is about and all of that, maybe I can pose a challenge for you, which is now that, of course, you could be called the expert in this area, then how would you start thinking about how your technology or your future technology will affect society in the future? Like having your mindset of your class and applying it to your specific research?
Yeah, no, that's a really good question. I think one of the things that I worry about is carbon in the atmosphere, right?
Okay.
CO2, right, which is causing global warming. And 10% of the global warming comes from electronics. It comes from semiconductors. So
10% of the
10
carbon that
of the carbon is released
produce.
the anthropomorphic carbon is produced by electronics.
Produced by humans, yeah.
By humans,
Anthropomorphic,
right, produced by humans. So, and the reason why a lot of that energy is necessary is because of the resistance of these contacts.
Okay.
So if I can drop the resistance of the contacts, then I can reduce the amount of energy it takes to operate a semiconductor, which means that I can reduce the amount of carbon emissions associated with the production of the energy associated with that carbon, associated with that operation of that device. So in a sense, it's a distant, it's not an immediate impact, but it does have an impact. The more we reduce the resistance, the less energy we have to use to operate these devices. And in theory, then, if we're using a non-renewable resource to create that electricity, right, then we're not gonna have to use as much of it. So that could have a profound impact, right? I think people all too often ignore the amount of energy it takes to run these clouds, to run the server, right?
Yeah.
And they just think it's just all free and out there and everything else, but it actually is impacting our environment, right? And
Yeah,
so
and
that's
even people using those servers to,
right.
for example, mine cryptocurrencies,
Right,
which has
right,
been a
yeah, which
recent
is really,
problem.
yeah, that's a whole different piece. But you're absolutely right. I mean, that's you know, when you start thinking about the energy you're using to do that, that's kind of counterproductive. So, but yes, I think that's a small but subtle way of trying to impact what's going on out there in the environment.
And do you see any negatives that could potentially come out of your
Oh,
research?
I think anything can be potentially abused, right?
Mm.
I think that's for us as people to make sure that we make the right decisions, right? When you start talking about artificial intelligence or where you're going to go with that, you need to make sure that you're using it for the right reasons and the right things. I mean, there've been a gazillion movies, made of
Showing the negatives, yeah.
the computer takes over and the nuclear weapons and decides to launch an attack or whatever, right? And so everybody always has a doomsday scenario about these things. But I do think that it's much more along the lines of thinking about making sure that we have good social understanding of what our innovations are going to do, right? And so that we don't create stuff that we turn around and regret somewhere down the road, right? So we think about what we're doing when we do it, right? And I think
Yes.
that's the thing that I would say is the most important thing, because anything can be used negatively. So you have to make sure that you try your best to, you don't stop innovating, but you also want to make sure that you innovate in directions that will better humankind, not hurt it.
Yeah. Yeah. And I was going to ask you actually about advice that you could provide to students since you've had a pretty long career and successful career. Is there
Um,
is there advice that you can provide to students when they're starting, and not necessarily engineering students?
yeah,
Just
I think the advice I've got is just, it sounds like a country song or something. It's all very classic stuff, right? I think it's be passionate, be I would take a motivated student over an intelligent student any day. I've seen lots of very brilliant students who were not motivated, and I couldn't do anything with them, right? But if you give me somebody motivated, then I can work with them, right? And we can do great things together. So I think bring your passion, bring your motivation uh, to the project, because life is short, and if you're doing something you don't like, then don't do it, right? But do stuff you do like, right? And that classic line, if you do what you love, then you'll never work a day in your life, kind of thing.
mm-hmm.
And so just do what really strikes you as something interesting, right? And that you can look back on in 40 years and say, I'm proud I did that, right? Or I think I've contributed somehow to making it a better world. And so I think in that sense, finding your passion, because I think if you're passionate about it, then you'll be successful, whether it be in art or whether it be in music or whatever it is, right? I play a lot of frisbee, ultimate frisbee, and very few of them are engineers, right?
Mm-hmm.
But I see their passion in their arts, and some are musicians and things like this, and when they're passionate about it, they just love it, and that's what's great about life.
Yeah,
That's what's really
and you
good.
can, if you're passionate enough about it, you can figure out ways how to monetize whatever that passion is,
Right,
and provide for yourself,
right,
right?
right, and
And
survive
yes,
doing it.
exactly, which
Right.
is important.
Right, right. So I think that's the thing is just find what you love to do, and then be really committed to being passionate about it, right? Not just kind of dipping your toe in the water and maybe I kind of sort of like to do this, or I want to do this because my roommate did it, or whatever it is.
Mm-hmm.
Find out what it is that really gets you going, and go do that. So
And you mentioned life is short.
yeah.
Is there things that you're grateful that you've had over your life and that you have now?
Oh yeah, I mean all the classic stuff. I have a wonderful family. I have three brilliant children, so I'm always really proud of them, and a couple of great little grandkids now. So I think that's wonderful, and a wife who's been extremely understanding about all the stuff that I do, because I have all these crazy passions. I played ultimate frisbee for 45 years or something, 42 years, and I still play, and so it's just one of those passions. And I love to fish, and I love to garden, and I like to do woodworking, and so it's so you just find things that you like to do and go do them, right? And so I think I think as long as you're doing something you're happy with, then you're going to be happy, right? And you just go off and do that. And so I think you just don't stop, right? You don't, it's, what is that saying is that you don't stop playing because you get old. You get old because you stop playing, right?
I like it.
Yeah.
I like it.
And that's very true.
Yeah, try to have that mindset for sure. Yeah,
I think that's a really good mindset to have, right? There's people have these dictations that's like, oh, you've gotten to this age, you have to stop this thing. It's like, no, you don't. Just keep doing it, right? Look at Tom Brady.
You can still have fun, right? You can still play.
Still doing it. Yeah, you just find it. Maybe you're not the best at it anymore, but you don't care. You're out there to have fun, right? And so if you really want to only do it while you're at the top of your game or whatever, then it's going to be a very short career, right? So I think that's part of it. Is find something that you love to do and find friends, good friends. Keep them close, right? I mean, I read some statistic. They said the other day that because of the internet, we have fewer close friends than we used to.
Yes.
Right.
Yes, I've seen that too.
And I find that very disturbing, right? And the way they define a close friend.
And your friends might even if they're close, they might be digital friends.
Right. Yeah. They're and I think it's we used to have I can name 5 or 6 people that I would consider super close friends. That if they called up and said, I need you here, I'd jump on a plane in 10 minutes and be there, right? And if they needed to borrow money, I'd lend it to them without hesitating, right? And I think that's interesting that you don't get that kind of connection with a digital thing as often as you do just from sitting down with people or sharing an experience with them.
I think so.
So I think that's maybe what's missing is that we get kind of caught up in the digital world and we forget to go out and actually experience the world and actually do things and have fun with them, right? And develop those friendships. So I think that's something that's important. And those people are the kind of people that, you may not talk to them for 15 years. And when you talk to them, you'll pick up the same conversation right where you left it off 15 years ago, right? It's like, you just go right back into it. And that's a really special thing to have. So anyway.
Well, yeah.
All right.
I think we've been going
at it
for a lot. So
yeah.
Thank you so much for your
time.
time.
You're welcome. Yeah, it was wonderful talking to you. Good luck with your podcast. You engineer inherently to help society. So society is going to influence your engineering, right? We make things to help people, right? And so we're not making things to not help people. We're making things to kind of change society for the better.